Hi, good morning. Today we are going to start our new section Operators of Finite Rank. Just to look at the title Operators of Finite Rank. We already discussed about bounded linear operator. Now we are going to discuss operators with rank finite. Actually, what is mean by a rank? We already know if it is a linear transformation from V to W. Now what is the rank of T? By definition, rank of T is actually dimension of image of T. Okay. So here also same definition. Here we are considering bounded linear operators. Okay. Let A be a bounded linear map from X to Y. Okay, then we call dimension of image of A as rank of A. Okay, already know. Same as a linear transformation. Okay, now we call linear transformation is of finite rank. We denote this as this rank as rank of A. Okay, rank A. Here notation is rank A. Okay, in linear we have like this rank of A. Okay, here notation is like this rank A equal to dimension of A, and A is of finite rank. If rank of A is strictly less than infinity, then we call A is a finite rank. Okay, now we are moving to find an example of a finite rank. Okay, if A is a finite rank, then we call it as a finite rank operator. Now, what do you mean? Give an example of a finite rank operator. That is our first problem. Okay, so we consider the space x and y. Okay, x and y, and x and y are Banach spaces. Okay, so you choose some finite number of elements in y. Okay, let y1, y2, etc. yn belongs to y. Any element, some elements. Okay, and you choose some fi belongs to x star. Okay, x star means it's a linear function. Fi is a linear function. So y1, y2, etc. yn belongs to y, some elements. Okay, and the f5 belongs to x star. So we can correspond actually f1, f2, etc. fn. Okay, these are belongs to x star. Clear? Now we are defining an operator. Now we are defining an operator ax. Ax is equal to, here we are defined like this, sigma I equal to 1 to n fi of x into ya. This is our definition. Let's look at this definition. What about fix? Fi belongs to x star. Therefore, what about fi of x? For any x belongs to x, fix clearly belongs to k. Fi's are linear functionals. Okay, so actually our ax is some, this is equal to some I equal to 1 to n, some ciya. Actually, this is a linear combination of elements of ya. Okay, now we are going to prove this A is of finite rank. Okay, before that we have to prove A is linear. Okay, so you choose some alpha belongs to K and x comma y belongs to x. Okay, now by definition A alpha x plus y is equal to, what is this? This is actually sigma I equal to 1 to n fi of alpha x plus y. Okay, into ya. Clear? And this is equal to, but fi's are linear functionals. This is equal to fi of alpha x plus fi of y and whole ya, and this is equal to sigma I equal to 1 to n fi of alpha you can write as alpha fi of x into yi plus fi of y into ya. and you can replace sigma. That's your sigma I equal to 1 to n fi of x into yi plus sigma I equal to 1 to n fi of y into ya. Okay, and this is equal to alpha. This is actually ax plus ay. This implies A is a linear map. Okay. Now to prove A is linear, A belongs to it's a bounded linear operator. We have to check mode also. Okay. Now here from this clearly A is a okay. Now we'll check A is bounded. Okay. Now what is norm of Ax? By definition, norm of Ax is equal to what is Ax? Norm of sigma I equal to 1 to n fi of x into ya. Okay. And this is equal to, this is actually less than or equal to sigma I equal to 1 to n norm of fi of x into ya. Okay, and this is less than or equal to sigma I equal to 1 to n norm of fi into norm of ya. Okay, norm of ax less than or equal to, but what is norm of a? Supremum of norm of x such that norm of x. Therefore, clearly each term is less than or equal to this one. This implies supreme also. Norm of A is less than or equal to sigma I equal to 1 to n norm of fi into norm of ya. This implies each fi is a linear function, bounded linear function. Therefore, this is less than infinity. Ya belongs to y. Y is a Banach way. Therefore, this is also less than infinity. This implies norm of A less than infinity. This implies A is bounded. Okay. Now we have to prove A is of finite rank. Okay. So we have Ax is equal to sigma I equal to 1 to n fi of x ya. Okay. As I told earlier, this is actually equal to sigma I equal to 1 to n some ci or ki. Okay. Ci ya. Therefore, A of x, if you take any element in image set, A of x is linear combination of finite number of elements. Okay, all these are linear combination of finite number of elements. A is a map from x to y, yi belongs to y, and each ax is a linear combination of y. Therefore, clearly dimension of rank of A, dimension of image of A is clearly strictly less than or equal to n, because each term is a linear combination of ya. Okay, y1 y2 etc y. Therefore image of A is contained in a span of y1 y2 etc ya. Okay, therefore dimension of image of A is less than or equal to n. This implies A is of finite rank. Okay, let's begin. A is a bounded linear operator and it is of finite rank. Now our next aim is to find dual operator for A. Okay, now what is dual? Dual of A. What is dual? By definition, definition of dual, we have phi of Ax is equal to A star phi of x. Okay, this is our definition of dual. Now what about here phi? Here Ax, okay, you just apply phi for Ax. And this is equal to phi of, what is our Ax? Sigma I equal to 1 to n fi of x into yi, and this is equal to sigma I equal to 1 to n fi of x into phi of y. This is actually phi of fi of x ya, but fi of x is a constant, therefore we can take this outside, therefore this is equal to this. Okay, and this is equal to sigma I equal to 1 to n fi of x, sorry, this you can write as phi of yi into fi of x, and this is same as sigma I equal to 1 to n phi of yi fi of x. Therefore, this is actually equal to, we get phi of ax is equal to a star phi of x, a star phi of x. Okay. Therefore, a star phi is equal to, therefore, a star phi is equal to, a star phi is equal to, we can write as sigma I equal to 1 to n phi of yi fi. Okay. Thus we have ax is equal to sigma I equal to 1 to n fi of x into yi, and a star x is equal to, a star phi is equal to sigma I equal to 1 to n phi of yi into fi. This is our notation. If x equal to fi of x yi, a star phi is equal to phi of yi into fi, and we can write this notation as like this. We can mark this as, here we can mark a star phi star a of dot equal to sigma I equal to 1 to n fi of this yi. We put dot in place of variable x. Also a star phi, a star here phi equal to, actually this is of phi of yi into fi. Here dot is replaced by phi. Okay, just look at our definition. This is our definition, and we'll get this one. Okay, and we are denoting this representation as a equal to, we write a equal to sigma I equal to 1 to n fi of fi, this I don't know what to read, this symbol into yi, and this notation is called tensor product. This notation is called tensor product. Okay, so what is ax? Ax is sigma I equal to 1 to n fi of x into ya. Okay, so this notation is here written like this, fi of fi into ya. Here actually this is multiplication and circle. Okay, I will check and will tell you later what we call this notation as. Okay, this is tensor product. Okay, so we can use similar notation for a star is a star also. Okay, so if we apply x belongs to x, we get ax equal to fi of x y. Okay, here fi applies to x. Okay, and if we apply psi belongs to phi star, y star, we get a star phi equal to phi of yi fi. Okay, because now phi acts on yi. Okay, in this way, the same form of writing describes both operator a and a star. Okay, ax equal to fi of x y and a star phi equal to phi of y into fi. Here fi acts applies to x. Here phi acts on y. Okay. So for both a star and a, the tensor product is similar. Okay, this is sigma I equal to 1 to n f tensor product of fi and ya. Okay, Now we are going to prove one problem. First one is prove that every operator of finite rank may be written as tensor product. Okay. Okay. So now what is the solution? Suppose A is a finite rank operator, bounded linear operator of finite rank. Suppose rank of A equal to rank A equal to n. Now what is the meaning of that? We can dimension of image of A equal to n. Okay. Suppose image of A is equal to L. So dimension of L is equal to, thus we get dimension of L is equal to n. So what about basis of L? Let y1, y2, etc. yn be a basis of L. So corresponding to each basis means linearly independent set. Okay. So we have given any linearly independent set x1, x2, etc. xn. There exists a fy's in dual. We have one result in by orthogonal system. Okay. This was our result. Let x1, x2, etc. xn belongs to x, linearly independent subset of x. Then there exists f1, f2, etc. fn belongs to x star, such that fi of xt equal to this one and x you can write like this. Okay, we have this result. So similarly, if you apply y1, y2, etc. yn is a basis. Okay, y1, y2, etc. linearly independent system. Therefore, correspondingly there exists y1 there exists y1 star, y2 star, etc. yn star. Okay, all this belongs to y star. Okay, and such that you can write any y as y, you can write as here any x as sigma I equal to 1 to n fi of x xi. Okay, fi of x are dual map. Okay, and xi is from linearly independent set. So here any y you can write as sigma I equal to 1 to n. For fi we can replace yi star of y to y. Okay, so any y belongs to y you can write like this. Okay, so in particular you can write ax as, what is ax? Ax equal to sigma I equal to 1 to n yi star of ax y. And what is this one? This is equal to sigma I equal to 1 to n. We have phi of ax is same as a star of phi of x. Okay. Therefore, this you can write as a star ya star of x to y. Okay. So this is same as, if you replace fi is equal to a star yi, then we can write ax sigma I equal to 1 to n fi of x into y. And this is actually same as sigma I equal to 1 to n tensor product of fi and y. Okay. Now what about norm of fi? Clearly norm of fi is less than or equal to norm of a star into norm of y. Okay, therefore fi's are bounded linear functional. Therefore we can write any finite rank operator in terms of tensor product of, in terms of tensor product. Okay, Now we are going to prove one problem. The problem is prove that every bounded operator of finite rank is a compact operator. Okay, so we have a result. Let A be let A be a bounded operator of finite rank. Okay, now using the previous result, any bounded operator you can write as Ax is equal to sigma I equal to 1 to n A star yi star of x into y. Okay, and this is equal to sigma I equal to 1 to n. We can write like this fi tensor product of fi and y. Okay, where fi is equal to a star ya. Okay, also norm of fi is less than or equal to norm of a star ya star. Okay, so clearly norm of ax is less than infinity also. Okay, is a bounded operator. Okay, so to prove our result we need one result. We are using this result. Any bounded set in Rn is relatively compact. Okay, so let's move to the proof. We have to prove A is a compact operator. Okay, to prove A is compact, it is enough to prove that. What we have to prove? We have to prove what is the definition of a compact operator? What's the definition? A from x to y is compact if every bounded sequence xn belongs to x, axn has a Cauchy subsequence. And we have another result. If A is a compact operator if and only if image of a unit ball is a pre-compact set. So here we are going to prove image of a unit ball is pre-compact. Okay, let x belongs to x be such that norm of x less than or equal to 1. And here we are going to prove image of set of all x belongs to x such that norm of x less than or equal to 1 is a pre-compact set. Okay, this is what we are going to prove. Now what about ax? Image set is ax. Okay, so image set is ax, that is here actually we have to prove set of all ax such that norm of x less than or equal to 1 is pre-compact. Okay, this is what we have to prove. Okay, so what is here ax? Here ax is actually sigma I equal to 1 tensor product of fi and yi, and clearly A is a bounded set. Clearly image set is a bounded set in a finite dimensional subspace. Okay, because ax you can write as sigma I equal to 1 to n tensor product of fi and yi where fi of x into y. Okay, so clearly this is a subspace of a Rn because y1 y2 etc linear. Okay, also it is a bounded set. Any bounded set in Rn is relatively compact. Therefore, image set is relatively compact. This implies A is a pre-compact set. Okay. So just to revise what we have discussed today. Today we have started our new section, finite rank operator, operators of finite rank. Now what is the definition of a rank of A? Okay, what is rank of A? Rank of A is the dimension of image of A. Okay, and we have discussed one example of a dual, one example of a finite rank operator. Then we find that it's dual, and we have denoted this A as sigma I equal to 1 to n F tensor product of Fi and Yi. Okay, and then this is a okay. Then we have proved every bounded operator of finite rank we can write as a tensor product. And finally, we have proved every bounded operator of finite rank is a compact operator. Hope everything is clear for you. Okay. In the next class, we will discuss compactness of integral operator in L2. Okay.